the 2025 AMC 12B problem 21. Two non-congruent triangles have the same area. Each triangle has sides of length 8 and 9, and the third side of each triangle has integer length. What is the sum of the lengths of the third sides? Okay, so let's try to draw a diagram here. So we have one triangle that has lengths like 8, 9, and let's call this third length here x, or I'll call it A actually. And then we have a second triangle. So it has like a different angle to it, maybe. So this one we'll call the hypotenuse length B. So they each have different angles here, right? So this one we can call theta 1. This angle we can call theta 2. So if we know, we don't know the third length of the triangle, but we do know the two sides of the triangle. So we can try to use the sine angle formula to try to get some information about what these two angles should be. So if we do that, we know that the area of this triangle is going to be 1/2 times 9 times 8 times the sine of theta 1. And this triangle is going to be 1/2 times 9 times 8 times the sine of theta 2. So what we notice here is if these two triangles have the same area, then these two sine values must be the same. And furthermore, we know that the two angles cannot be the same, right? Because if they were the same angle, then by SAS congruence, these two triangles would be congruent, right? So if the two sides were equal, the two angles were equal, the second sides were equal, then they must be congruent triangles. So therefore, the two angles have to be different. So we have two angles that are different, but their sine values are the same. And if we recall, the way the sine function looks, right, from 0 to pi, it's like a curve, like that goes up and then back down to pi. Or I'll just use 100. I'll use degrees instead of radians for simplicity. So 180 degrees, right? So if we have like theta 1 over here, right? This is sine theta 1. Then the other angle would have to be 180 minus theta 1. So basically, if you have two angles like of a triangle whose both of their sine values have to be the same, but they're not the same angle, then they have to be across from one another, right? On like this range of the function from 0 to 180, right? So theta 1 and theta 2 actually have to add to 180 degrees. If this explanation wasn't convincing enough, there is another proof of that this works. So basically, we can draw a parallelogram. 8, 9, 8, 9. And this is a parallelogram. So these angles are equal and these two angles are equal, right? And in particular, we have like two triangles that like that would work for this problem, right? So we have this triangle, 8, 9, and this side, and we have this triangle here. So these two pairs of triangles, right? We have a 8 and 9 as the side lengths, and they each have the same area. And in fact, their angles are 180 minus each other, right? So the reason why these two triangles have the same area, by the way, is because they're half of the parallelogram. That should be pretty clear. They're both half the area of the full parallelogram. So therefore, in general, when you have these two angles add up to 180 degrees, that means that the two triangles have the same area. So basically what we get out of that is that this angle is theta 1, or I'll just call it theta from now on. And the other angle, I'm just going to call 180 minus theta. So now that we know this relation between the two angles, the next step would be to use the law of cosines, because we now know information about these two lengths and the angle in between, and we want to find information about the third length. So we use the law of cosines. So if we do the math, right, we have that a squared is equal to 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of theta. And b squared is going to be equal to 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of 180 minus theta. And now we can think, what is the relationship between cosine of theta and cosine of 180 minus theta? Well, it's very similar to the sine relationship where they're equal, except instead of being equal, they're actually going to be inverses, right? So if we think about what the cosine function looks like from 0 to 180, it looks like this. So it goes down, it flips. Oops, that's not okay. Like this. It flips directions. So any like angle here, if we have like theta, and then this is 180 minus theta, we can see that since it like it's rotationally symmetric with respect to the middle, these are going to be inverses of each other. So essentially what that means is that we can take this and replace it with positive 2 times 8 times 9 times the cosine of theta, right? Because when we replace cosine 180 minus theta with cosine theta, that has the effect of multiplying it by -1. So the negative becomes positive. Okay, and now you can pretty clearly see exactly what we need to do here, right? So in particular, we never figured out what theta is because there is really no way for us to figure out what theta is. But these two equations here, they give us a way to eliminate theta. So now we don't have to worry about an angle that we have no idea what its value is, right? So we can add these two equations together, and that will give us a squared plus b squared is equal to 2 times 8 squared plus 9 squared. So now we just have to find two perfect squares that sum to this value here. We can just calculate out this value. We're going to get 290. And there are multiple different ways to solve an equation like this. If you know about like the sum of squares identity, you can do it that way, where like we can break this up into 10 times 29, and then we can write that as 1 squared plus 3 squared times 2 squared plus 5 squared. So it's very easy to write these as sums of squares. And then you can just do the like, there's this identity that states that the product of two sums of squares can be rewritten as the sum of two squares like this. So we can write it as 3 times 5 minus 2 times 1 squared, or rather plus or minus. Yeah, plus or minus this squared plus, and then 3 times 2 minus or plus 5 times 1 squared. This is like the sum of squares identity. Then this is like a clean way to solve the problem, but you can definitely, since 290 isn't a very large number, you could definitely just brute force possibilities for like each of these numbers from 1 up to like 15 or something and find the solutions that way as well. But I'm just showing an elegant way to solve it. So by the sum of squares identity, we get that we can write it as, well, if we use the plus and the minus here, what we'll get is 17 squared plus 1 squared. That's one way to write it. Or the other solution is going to be 13 squared plus 11 squared. And so now we're looking at this, and what you might think is, oh no, we have multiple solutions, right? So in particular, we have that A and B, they could be like 1 and 17, or they could be 11 and 13. So how do we know what the solution would be, right? What was the answer, both 18 and 24? Well, no, there's only one answer. And if you have looked at this, hopefully you've seen that 1 and 17 are nonsense answers because by triangle inequality, 8 plus 1 is not greater than 9. So this is going to be like a flat line, a degenerate triangle. So it's in general on the AMC, like flat triangles, degenerate triangles are not considered triangles. So if you have like a flat line here and we have like 1, 8, 9, and these are like the three vertices, this is not considered a triangle. So therefore 1 and 17 is an invalid solution. Also 17 is 9 plus 8. That's another way to look at it. So this is a completely invalid solution. So the only valid solution is 11 and 13. And that will give us the correct answer of 24. If you qualified for AIME, make sure to check out our latest AIME book preparation of 5 practice tests to help continue your Math Olympiad journey.